Good afternoon. My name is Dwayne Brown with NASA's Office of Communications. Welcome to NASA headquarters. Today you will hear new details about the structure of solar storms and also hear how they impact here on Earth. Today's briefing materials are on the internet at www.nasa.gov/stereo, in addition to www.nasa.gov/sun-earth, all one word. We'll have brief presentations from our presenters, then we will open it up with questions starting here in Washington, our NASA centers, and the phone lines. I'd like to introduce you to today's participants. First up, Lika Guha-Takurta, lead program scientist for NASA's Living with a Star program and also program scientist for Stereo. Craig DeForest, staff scientist, Southwest Research Institute, Boulder, Colorado. Dave Webb, research physicist, Institute for Scientific Research, Boston College. And Elisa Reinert, research scientist, National Oceanic and Atmospheric Administration in the University of Colorado, also in Baltimore. And with that, I'll turn it over to Lika.
Thank you, Dwayne. Stereo is a mission in NASA's heliophysics division, and heliophysics is an emerging new science discipline. The goal of this division is to understand the sun as a magnetic variable star and its effect on Earth as well as the entire solar system. As you might know, we live in the outer atmosphere of this star, which at times can be stormy and turbulent, giving rise to the phenomenon of space weather that we hear about so often these days. So the three main objectives of this division is to really understand the basic plasma physics processes from sun to Earth and the solar system, which is vast, very complex, very dynamic, to understand the physics of the interaction between sun's magnetic field and Earth's own, which is where space weather phenomenon is felt, and then also to develop the scientific understanding necessary to really create these forecasting capabilities of these extreme dynamic conditions in space that is experienced by human or robotic explorer, wherever we choose to go. This is accomplished in a variety of ways. We have a research portfolio along with a set of flight programs that provide unique observations from really strategically located vantage point, which is very important for gaining the physics understanding that we are seeking. The flight programs are three. The Explorer program, which are typically small missions led by individual principal investigators focusing on a subset of very small questions to which we can find scientific answers. Then we have two strategic lines, Solar Terrestrial Probe, and that goes after really science questions for science sake, and Stereo mission is actually part of this program. And finally, we have Living with a Star program, which is another strategic flight program line, where we actually look for missions that have really go after cutting-edge science, as well as look for relevance to life and society. Solar Dynamics Observatory is an example in that category. If I could have the first systems observatory slide, what you're looking at there is the Heliophysics Systems Observatory. We call it Evolving Heliophysics System Observatory because we are continually retooling it, replenishing it. And so the white satellites there are our operating missions, and the ones in yellow are really our future missions that we are developing right now. There are about 16 such operating missions. And so just looking at that, you realize that we have been studying this system for a while. But it is a really vast distance and a very complicated dynamic environment. So just a decade or two is not sufficient to fully understand this system. And so what we try to do is we try to bring in new missions which lend to new scientific insights and retire some of the old ones from which we have already gained the science understanding that we need. And in this context, I think stereo is playing a really vital role with its imaging capability as well as its in situ measurement capability. What you also see in this picture, what might appear to you, is that there are just a large number of spacecraft. So just to kind of give you a perspective, the distance between the sun and Earth is 93 million miles. Well, it's not really obvious in this picture, but if you can imagine the sun being the size of a basketball, in comparison, then the Earth would be like a pinhead. And now you take these two objects and you put them at the two extreme ends of a basketball court. That's what you're looking at. That's the distance. And if you think about it in that terms, then these few satellite observations are really nothing. It's like measuring the ocean currents with just few buoys. And it's very difficult to get a full perspective of the ocean current if you're trying to do that. So you understand the enormity and the complexity that we are trying to understand with these satellites. And what stereo is doing is really with its imaging instruments, it's actually giving us a perspective on the turbulent solar wind and solar storms. And it is really giving us a picture which is a global image which replaces sort of the buoys in some sense. If I could have now a picture of the stereo perspective, and what stereo mission was launched about 5 years ago, October of 2006. The two spacecraft kind of launched from Earth orbit, and one spacecraft known as Stereo A, not a very imaginative name, but it's kind of leading the Earth orbit. Stereo B is lagging behind, and they are drifting at a rate of about 22 degrees per year. And what these two spacecraft do is initially they gave us a three-dimensional view of the solar wind and solar storms, and as they drift away now, they give us unique vision of the storms that are coming towards us. And the picture that you see is essentially a schematic cartoon of the particular storm that we are going to discuss in detail in this press conference, which took place in December of 2008. The two stereo spacecraft had an angular width of about 45 degrees. Stereo 2 spacecraft achieved its opposition, meaning they were 180 degrees apart in early February of this year, and they continue to drift. They will eventually go behind the sun, but today they are about 164 degrees behind. So just 5 years ago, if you think about it, solar wind was largely invisible to us. We could measure it with our spacecraft like ACE and WIN at Earth orbit. And solar storms could be viewed with spacecraft like SOHO very close to the sun. With Stereo's 5 telescopes today, we are actually witnessing the solar wind. We can see them, solar wind and solar storm blowing all the way from sun to Earth, which is pretty incredible when you think about it. Sheer observations from stereo have improved our ability to predict arrival of solar storms at Earth hugely, and you will hear about it in detail a little bit later. But the physics knowledge that we have gained from such observation is pretty impressive too. Now, what you have to remember that we are now able to provide constraints for our models. Models need input, data input, like density, velocity, magnetic field strength, its direction, shape of these structures, which really give us a sense of the magnetic topology that bound these structures. And with these, we are actually able to do much better modeling. And that is really very important. You know, sometimes we've seen many solar storms, and you think maybe all of them are traveling and arrive at Earth. That's not the case. a lot of stuff goes on between the sun and Earth. Some solar storms are kind of deflected or eaten away by solar wind. Some storms actually speed up in their transit. Some slow down. Some storms have their structure kind of distorted by the environment of the solar wind that they are traveling through. And so and stereo is actually observing all of this, all the way from the beginning to the end. And so to give a really detailed description of one such storm is Craig DeForest.
Thank you, Lika. So the news today is that for the first time, we've been able to image a coronal mass ejection with lots of detail and of photometric quality all the way through its entire life cycle, from the inside of the solar corona until it impacted the Earth 3 days and 93 million miles later. Now, this was enabled by new processing methods that were applied to archival data from the International Secchi instrument, onboard stereo. So I'd like to introduce a movie of the science. We've combined 5 separate cameras' views into one frame. And I'll just give you the movie to start with. So if we could roll the science movie here. On the right side of the frame, you see the lower solar corona, and you'll see a coronal mass ejection form down in the corona and be launched into space, crossing the entire solar system until it becomes a 50 million mile high wall of plasma about to envelop the Earth. Now, for a sense of scale, the Earth on your screen would be microscopic. We've actually drawn a little icon on there because you wouldn't be able to see it otherwise. The scale of these events is simply immense. For the first time, we're able to actually track through these outer regions of the image here on the left-hand side in black and white as the structure evolves and distorts before impact. So for 40 years or more, we've understood that the sun occasionally hurls billion-ton clouds of material at 1 to 3 million miles an hour into interplanetary space. When those clouds impact the Earth, they cause space weather effects that affect our technology, cause auroras, that sort of thing. But until now, we couldn't see any detail in these structures after about 10 degrees from the sun. And the result is that everything outside of that has been extrapolation. So we've been unable to connect the very detailed structures we see at the Earth back to the solar structures that gave rise to them in the first place. But now, we can identify which parts of the CME came from the sun and which parts were swept up from the solar wind in its path. We can see how the CME is modified as it propagates and grows across the solar system. And we can get a first look at how the magnetic structure that drives the CME changes and evolves as it pushes the bright material in front of it, sweeping up solar wind to impact the planets or spacecraft that sample it. So to track CMEs, we've been mentioning there are 5 cameras that we have to combine, and they have vastly different scales. So I'd like to show you what we did to prepare these images so you could see them. If we could roll the zoom movie, please. We begin with an ultraviolet telescope image of the sun. We zoom out until we can see Venus and the Earth more than 45 degrees away from the sun. However, we can't see the corona. So we've distorted the coordinate system into radial coordinates, which allows us to see the entire system in one screen. The scale changes drastically from the right to the left. On the right-hand side, we have the sun. On the left-hand side, we're looking at whole planets and the distances between them. Now, the outer cameras, the outer 4 cameras in that field of view, the sepia tone and the black and white, measure ordinary sunlight that's been scattered off of free electrons in the plasma clouds in the solar system. Close to the sun, that light is easy to measure. It's relatively bright compared to the stars. But by the time the cloud reaches Venus, it's 10 billion times fainter than the surface of the full moon. It's about 1,000 times fainter than the galaxy or the star field in deep space behind the images. So it was a tremendous achievement to separate the 2 signals. It was very difficult to separate the signal from the clouds from the star field that's superimposed upon it. It's a testament to the quality of the instruments from NRL and the Rutherford labs that we're able to drill this far into the data and actually find something there at the bottom. So moving back to the science, let's review the data that I showed you at the beginning in slower motion. Now, pay close attention, not just to the bright front as it sweeps across, but to the dark void behind it. And I'll narrate as we run the gauge movie here. So again, we'll see the event form in the lower corona. It's visible in the ultraviolet. And we'll see it propagate through the brown-toned lower corona and out into the heliosphere, growing and distorting as it moves. You can see the dark region behind the front is full of magnetic field, and that's what's driving the event. As it picks up material from the surrounding solar wind and gains brightness in front, the magnetic field, the magnetic flux rope that's doing the pushing, distorts. When the whole event hits the Earth, the wind gauge pegs at 20 atoms per cubic centimeter and then returns back to normal levels, indicating that, in fact, we are measuring the appropriate thing. That gauge is driven by in situ measurements from NASA's WIND spacecraft that was actually at the Earth and detecting this event as it went by. So to sum up, we have for the first time, we've tracked a complete CME life cycle from the interior of the corona out to the Earth. This was achieved by reprocessing existing data from really stunningly high-quality archives from stereo. And this should give us new insights into how solar storms evolve and connect the events that we can measure at the Earth back to their solar origins. With that, for more context, I'll hand you over to Dave Webb.
Okay, thank you, Craig. These movies are very important to solar wind studies, especially those that involve the evolution and interaction of this material in the inner heliosphere. Heliospheric imaging itself bridges a gap between observations near the sun and those much further out at the distance of the Earth or beyond, as we've seen here. Now, the solar wind is a hot plasma which flows out from the solar corona of the sun and is guided by magnetic field lines that spiral out from the sun in a garden hose pattern because of the rotation of the sun. Now, if we could show the movie, this is a 3D simulation model of the solar wind and a CME moving out through it that was taken during the first 10 days of this month, August. This view on the left shows the circular view, shows the ecliptic plane, which is the plane that the planets move in around the sun. So it's looking down on that plane. You can see the curved dashed lines are these magnetic field lines that are rotating around with the sun. And the colors are the density pattern in this model. The brighter colors are denser structures. And the other view on the right is a north-south cut through the plane, Sun-Earth plane, showing you kind of the vertical component. And this is similar to the views that we're seeing from the HI images that Craig just showed. Now, the plasma can be compressed along the original field lines, so that'll give you a long curvilinear density structure, which co-rotates with the sun. Now, when the CME comes out, you can see that it distorts those field lines considerably. And the CME itself drags its own plasma and magnetic fields out into the heliosphere along with it. So these studies of the solar wind and co-rotating structures, as well as the CMEs and the interactions the CMEs make with these structures, all will benefit from this kind of imaging that we're seeing today. Now, we have been able to image the inner heliosphere before. In the 70s and 80s, 1970s and 80s, we had the Helios solar probes, which were in orbit around the sun. But they had a resolution that was much poorer in time and space than what we're seeing today. There wasn't another instrument like this until 2003, when the Air Force built and launched the Solar Mass Ejection Imager into Earth orbit. And, of course, then the stereo HIs we're seeing now were launched in late 2006. Data was taken early in 2007. So it was almost 4 years later. SME was very successful, but it can't view within 20 to 30 degrees of the sun. It has noise because it's in Earth orbit from particles and aurora in Earth orbit. And it's also nearing the end of its lifetime. Aside from SME and the HI instruments, there are no other telescopes right now that can view the inner heliosphere like we're seeing today. So these observations are now achieving a goal that scientists have had or worked towards for about 4 decades now. This goal was to observe and understand the basic structure of the solar wind. The observations allow us to separate CMEs from co-rotating flows, and also to better visualize and understand the different parts of a CME. For instance, the sheath region, which is plowed ahead of the CME as it's moving out through the heliosphere, has a density which is likely related to the strength of the CME following behind it. This has space weather implications that we'll hear about in a minute. Finally, these images will permit global views of the solar wind and CMEs and so forth when this data is put into various kinds of models, such as the one I just showed you. Now we'll turn it over to Alicia, who will discuss the space weather aspects.
Thank you. So I'm a researcher at the NOAA Space Weather Prediction Center, or SWPC we call it. SWPC is responsible for operational space weather forecasting, and so we complement the basic research that's done at NASA. They help us understand these events, and then at NOAA we try to forecast when one of these events will happen. And the reason we care is because when one of these CMEs, one of these coronal mass ejections, pass the Earth, they can cause problems with satellites. We've had a couple cases where power grids have been disrupted. GPS signals can be made inaccurate when these storms are passing. So it's good to know in advance so we can be able to warn people who rely on these technologies that there may be problems. The CMEs also cause the aurora, so they're not all bad. We have some good benefits from that. NASA helps us with our predictions by both the basic research to help us understand these events and by providing what we call beacon data, which is lower resolution data that can be beamed to SWPC forecasters instantly so that they can make their forecasts with the latest observations available. Now, before stereo was launched, we had the SOHO LASCO instrument, and that's how we observed our CMEs. And so if we roll this movie we have here, we can see some CMEs with LASCO. This was a very active time, so you see a lot of CMEs, these bubbles of plasma coming out in all different directions. Now, the forecasters use this to, we can measure the speed of these CMEs, but there are a couple problems. One of them is that the CMEs we care about are the ones that are coming towards us. And so because of the angle, it's a little more difficult to measure the velocity, and you also get these proton events like you can see here. The other problem is that SOHO images very close to the sun, and so you're only seeing the early stages of these CMEs as they're coming out. So you can measure the velocity, but the CME may speed up or slow down as it heads out towards the Earth. We have models that try to account for this, but they're still a bit inaccurate. We can get a window of about 12 to 14 hours of when we think the CME will get to the Earth. And of course, we'd like to do better than that. With the stereo HI instruments, with stereo, once stereo is launched, we have a couple of benefits. And one of those is that stereo is moving away from the Earth, so you get a side view of the CME, so you can measure the speed a lot more accurately. Also, with the HI instruments, you're able to image the CME as it goes out from the sun, much further out towards the Earth. And so just using these images as they were, we're able to improve our predictions to about an 8-hour window at the Earth. And we think that with Craig's technique, we can do even better than that, because now we're able to really see the CME all the way out to the Earth in detail and see a lot of the substructures. This is it's a big advance, and just to explain that, it's like trying to understand how a hurricane's moving across the ocean by just having a couple buoys that are measuring the wind speed, versus now these movies that we can see on the news of the hurricane actually moving across the ocean. So that's what it is to us, and now we're actually seeing the CME moving across the sky, and it's really it's amazing to see, and it really helps our predictions. So timing is very important, knowing when the event will get to the Earth. But the other thing is whether the CME will actually cause problems at the Earth, and that has to do with the magnetic field. So the Earth has a magnetic field that's called the magnetosphere, and it has a direction associated with it. And these CMEs have directions too. And the way to understand that is if you've ever played with a magnet, a couple magnets, if you turn them one way, they'll repel each other, and if you turn them the other, they'll attract. So if a CME has what we call a northward field, it's more likely, well, let's roll this next video, actually. So if a CME has a northward field, it's more likely to bounce off the Earth's magnetosphere. And here we have a CME. It's leaving the sun. And this one's going to have a southward field, so we can see what happens when that sort of CME hits the Earth. Here we're going to see these blue lines are the magnetic field of the Earth. And as the CME gets to the Earth, you see it's actually pulling apart the field, and it causes a chain of events which eventually lead to the aurora. And so obviously we want to be able to predict what the magnetic field of these CMEs are, and up until now we haven't been able to do that. But we have some indications that using Craig's results, we're able to link the structures of the CME with the magnetic field that we measure at the Earth. And we think that if we combine that with some additional observations, then we can start to make some predictions of what the CME magnetic field will be. Now, this is pretty preliminary. We need to do more study to be sure, but this would be potentially pretty groundbreaking. So, to sum up, this is a great result. It's very exciting and has important impacts for space weather research. And so now let me turn this back to Lika.
Thanks, Alicia. So you can see as we approach the peak of this next solar cycle, 24, maybe somewhere in 2013, we now have the necessary tools, data, and models to improve the physics understanding of space weather, which is what we are after. However, missions like STEREO are really science satellites, which will not always be there to provide us with these critical observations in the Sun-Earth system. That is why we invest in physics, understanding and modeling of this phenomenon. And heliophysics, system observatory kind of aid in that process. For example, we are now, as you heard earlier, able to verify models with ground truth verification at Earth from our measurements from our satellites like ACE and WIND. And in this plot that we have up there, that is kind of the same plot that I showed earlier, except now we have put all our operating missions and future missions on a solar cycle time frame. And so operating missions are 16 operating missions already going on. What you can see is that there are some future missions that's coming up that will continue to really retool our heliophysics systems observatory. Next year, we will be launching Radiation Belt Storm Probe, and that's 2 spacecraft that will be placed in Earth's radiation belt. This is the geospace environment, which is where we actually feel the impact of solar storms and is most important to us. And we will be trying to understand the consequence of a solar storm. And then in distant future, in 2018, NASA plans really a daring mission to the sun itself, and it is going to a mission called Solar Probe Plus that is going to go to the outer atmosphere of the sun, the corona, to really measure the particles and the plasma, much like we do with ACE and WIND at Earth, to provide that ground truth verification for our models, the beginning and the end. And this is the environment in which solar wind is created and solar storms propagate. So this is an exciting period in heliophysics. With that, I'll pass it on to you, Dwayne.
Well, thank you, Lika, and to our panelists. So we are now going to open it up for questions, and we're going to actually go to the phone lines first, and we're going to head out to the West Coast. And first up is David Perlman from the San Francisco Chronicle. David?
Yeah, thanks very much. And I have one two-part question. Do CMEs always originate within active sunspot regions? And then the second part of that question is, are any of you familiar with a report that's coming out in Science on Friday about the ability of a Stanford group to predict the onset of sunspots from the SOHO satellite that has been looking at the interior of the sun to actually predict the emergence of sunspots? And would somebody, whoever answers this, would you please identify yourself? Because I'm not in the studio audience.
Okay. Thanks, David. Craig, did you want to take the first question, or is that going to be Dave?
Sure. Oh, Dave will take that.
Okay.
Dave is here. As far as the what CMEs are associated with or come from back at the sun, many of them, especially the most energetic, are associated with active regions and flaring in active regions. But many are also associated with prominence eruptions or filament eruptions, which can exist. These are clouds of cool gas that exist in the solar atmosphere. We don't quite know why. They're suspended by the magnetic field. And for some reason, they can erupt. And when they erupt, they also can form mass ejections, coronal mass ejections. So these can also, active regions, of course, tend to be confined to the lower latitudes of the sun, whereas prominence can occur anywhere over the sun, even towards near the poles. And so, therefore, CMEs can occur anywhere from the low latitudes to the high latitudes. And near solar minimum, it's more towards the low latitudes. So this can vary over the solar cycle.
And that was Dave Webb speaking. Craig, did you want to add to that, or is that anyone want to add to that?
Second question, maybe.
Second question?
You want to answer?
Yeah. Like Dave said, the biggest CMEs do come from active regions most often, and so we do care about when there's an active region, when an active region may be emerging, and especially early on, right when the active region emerges, you can often get a lot of CMEs. I'm only partly familiar with this new research, but it is pretty exciting to be able to use helioseismology to look underneath the sun and try to predict when an active region will appear.
And I think I will add to that. I think this is one of the reasons we actually launched Solar Dynamics Observatory, which is the first mission of Living with a Star, really to understand helioseismology in greater detail and penetrate deeper into the convection zone where these magnetic structures are formed. And so SOHO MDI has given us the first cut of good statistics, and this result is actually going to be sharpened by using the Solar Dynamics Observatory's HMI instrument. So this is pretty groundbreaking. We are delighted to have this. We will have online press release on Monday. Stay tuned.
Craig, did you?
It's all
okay. Okay, and David, that was Lika talking. Then, of course, that was Dave and Alyssa. Okay. I'm going to get that right. I'm determined to get that name right. Okay. Next up on the call, Peter Spotts from the Christian Science Monitor. Peter?
Oh, thanks. Yeah, thanks for doing this. And actually, Dave scooped me on the question there. But I wonder if taking both of these results together, if you could just kind of place this in a kind of parallel context. I mean, how do these developments, as early as they are, but as promising as they are, can you think of a similar time, for example, in the history of weather forecasting, where you sort of had the same sort of potential breakthrough technologies coming along, just in trying to draw some kind of parallel for readers?
This is Craig DeForest. Really, you're looking at opposite ends of the same connected system here. The Stanford group is studying the origin of the systems that give rise to CMEs, and we're really studying what happens to the CME after it leaves the sun and propagates all the way out to the Earth. As far as a parallel with history, this really is like the beginning of space assets for weather forecasting. That for the first time, we're really developing systems that can get at the root, the structure of what's causing then Earth storms and now space storms around the Earth. So up till now, we've relied on point measurements and models, and really for the first time, we're beginning to see a complete predictive system emerging out of the science.
Did you have a follow-up, Peter?
Thank you.
Okay. Next up is Mike Wall from Space.com. Mike? Going once, going twice. Mike, are you with us? Okay. All right. Let me take a question from one of the .coms, and I believe this is going to be for all four of you all, so we just go down the row here. And The question is, with the public fascination of the sun, how can you personally tell the public on how we are more prepared and what we know about the sun from past, present, and future?
Well, we can tell a lot, actually. As I was indicating, that even 5 years ago, there were stuff we didn't know. And 5 years later, with observations from STEREO or Solar Dynamics Observatory, our whole view of how the sun behaves as a magnetic variable star is changing right in front of our eyes. So it is a really dynamic time in the history of heliophysics where our observations are ahead of our theoretical insights and understanding. But we are seeing these things for the first time, and we are grappling as to what is going on. So I don't know what more to say, but this is a very rich time for understanding heliophysics and space weather evolution.
Greg, your personal views?
Well, I have to agree with Lika that we're making tremendous strides. When I first got interested in this field as a boy, solar physics was sometimes referred to as dermatology because we could see features on the sun and not the interior yet, but we couldn't really understand them. And over the course of just my lifetime, we've seen the data get better to be where we're measuring the things we need to be measuring. And we've seen the models and data processing get better to where we can really encompass this phenomenally complex system. Plasma physics is extraordinarily complicated. The physics of solar flares involves differences in scale between things the size of Jupiter and things the size of this television studio. And encompassing that is just very difficult. And we've really seen a tremendous amount of this puzzle come together for the sun and by extension to stars in general, just in the course of a lifetime.
Well, see, the basic context, I think, for me would be I started out in this field in solar physics in the early 70s with the Skylab program. And at that time, we made many new exciting discoveries about looking at the sun itself in detail. Coronal mass ejections were kind of only discovered around that time, so that's 40 years ago. And since then, at that time, we knew nothing about how these things really connected with the heliosphere and the Earth and so forth. We could only make crude guesses at this. Now, with data like you're seeing today, we can actually, as I said, understand these things coming out from the sun, track them all the way to the Earth and beyond, and understand much better what they're what's happening with them as far as the systems approach goes. So we've made huge strides in my lifetime, or my working lifetime. It's very exciting to see this. And of course, now we have these future missions like Solar Probe, where we'll actually go into the atmosphere of the sun, and that'll be very exciting. So it's a very exciting time to be doing this work.
Alyssa?
Yeah, and I'd say that the work that I do, I sort of straddle the basic research that NASA does and the predictions that NOAA does by being based at NOAA. And so I can see both sides of this, and it's very exciting. So I echo what these guys have said, that this is a great time where we're getting all these new observations and this new understanding of how these events happen, and that's feeding into our forecasts and our ability to predict these in advance and predict how powerful they'll be. And as we become more reliant on technology, our satellites and everything become more and more important. That makes it more important to be able to predict when these events will occur. So it's an exciting time.
Okay, we're going to go back and see if we can take a second go with Mike Wall at space.com. Mike, are you with us?
Yeah. I just had a phone glitch. Can you guys hear me this time?
Read you loud and clear.
Okay, great. So actually, Stereo launched about 5 years ago. I was just wondering, why did it take until now for you guys to sort of be able to see this in this new way, to see all this data in this new way?
Well, I can address that. This is Craig DeForest. This is an extraordinarily difficult extraction problem, and we've highlighted the science that we've been doing more than the technique of extracting the data. But this is a very challenging image separation problem that we're looking these brightness clouds that you're seeing in the movie that's been prepared are fluctuations of less than 0.1% of the brightness of a starfield image. And so just a tremendous amount of extraordinarily careful work was needed to develop the algorithms. And many teams have worked on this. As with any science group, we have the final result, but we stand on the shoulders of giants who prepared the amazing instruments that can produce the data with this quality and did the groundwork of calibrating the instrument. So we need to recognize the folks at NRL and Rutherford Labs for producing such a terrific package.
Okay. I think that's going to do it for today. I want to thank you all for joining us today. Again, you could go to www.nasa.gov/stereo for